Hi, this is ME6008 6122 Microfluidics, and this is the last topic we're going to cover as part of our syllabus. It's on microscale gas flows. And our interest in gas flows is really where we get to see the kind of true microscale effects kick in. So what we've highlighted here, just about these microscale effects. So what happens? Well, gases undergo slip much more readily than liquids. And in fact, you can get slip effects occurring in gases in millimeter-sized channels. So it's relatively easy to see deviations from the classical continuum mechanics with gases. How does that arise? Well, it comes from the fact, essentially, that gases are dilute, that they're very well spaced apart. There's a lot of spacing between the molecules. And if you compare, we did this in class already, if you look at the density of a liquid, for example, it's of order 1,000 kilograms per meter cubed, whereas a gas, its atmospheric pressure and temperature is about 1 kilogram per meter cubed. So there's 1,000 times less in terms of density. And with that spacing between the molecules, they're much more compressible. And we start to see the molecular behavior or discrete nature of the fluid come into play much sooner. And what we're going to do in this lecture is kind of look at how we describe these effects. And we're going to cover the Knudsen number, and then we're going to look at the different models that are used for slip effects. And we're going to go as far as modified continuum stuff. So we're not going to go into full molecular stuff. So really, this is it's very much an introductory lecture in microscale gas flows. The topic itself will be a full course. So it's really just get you thinking about understanding what slip is and understanding the continuum behavior of the fluid, and when you need to start considering non-continuum effects, and then to look at the different models that we can use for slip. Okay, in terms of applications, who'd have thought that this thing would be so important nowadays? But respiratory flow, aerosols. If you think of the spread of COVID, it's in droplets, very, very small droplets that are inhaled. So in terms of biomedical applications, hugely relevant here. And in terms of industry, then in terms of process heat exchangers, microreactors, etc., also very relevant. Right, so let's just start off by looking at the discrete nature of the fluid. And gases are quite useful in this regard because they're relatively simple. Liquids are much more complicated things. They got much larger molecules and much more complex molecular interactions. So what it is, we consider simple gases that have a single chemical species and the same structure, and the easiest thing is just a sphere. So it's treated like a billiard ball or a ball bearing, for example. That kind of approach is very the simplest way that we can treat a gas. And you may have touched on this in a bit of physics before, looking at kinetic theory and things like that. So we've got three things that we're interested in. One is the mean molecular diameter, so a length scale that is representative of the size of the molecule. The mean molecular spacing, which is the distance between the molecules. And then we have this thing, which is the mean free path, which is quite important in terms of defining the Knudsen number, which is something that we'll come to in a while. And what the mean free path is the average distance that a molecule will travel before it hits another one. So it's different from the spacing. And if we just have a look at the next slide, there's a graphic that illustrates that to us. So we can see that here, delta is the spacing. And you can see that the distance a molecule, this one molecule here, has a collision, and the distance it travels before it has another collision with another molecule. Okay, so that's the mean free path. All right, so it's the average distance which the molecules travel before they undergo a collision with another molecule, which is different from the spacing of the molecules, which is the distance between them. Okay. We also have the number density, which is defined as the number of molecules per unit volume. Okay, so n is 1 over delta cubed. Okay, so delta there being the mean molecular spacing. All right, so that gives you a sense of the number density of them. Another way to think of this is in terms of 1 over n represents the mean volume available to one molecule. So how much space one molecule occupies approximately. Now, our definition for a dilute gas is that it is dilute if the spacing between the molecule is large relative to the size of the molecule. So d over delta is very much less than 1. And our mean free path can be defined in terms of the ratio of the mean thermal velocity, so this thing here, compared to the collision frequency, which is this. Okay, and the collision frequency we get from a model, a gas model, and the simplest one would be a hard sphere. And there's many different types. You'll see this on the next slide. There's a table of different types of models, and we won't go into the detail of all of these. You wouldn't be expected, but there's a lot of theory around these. And really, if you think of the hard sphere, is probably the most straightforward one. And we have a definition here for the mean free path for a hard sphere model. Okay, we also have the viscosity and the collision frequency there. Right, the mean thermal velocity then is the average speed at which it goes. Now, this is very easily confused with the speed of the flow, and they're very different. The molecules move a hell of a lot faster than the bulk fluid may be moving. So if you do some calculations, and it's worthwhile doing this, you can see it's proportional to the gas constant. So if you put in some temperatures, note that this is in Kelvin, and just run some calculations, you get some quite large speeds in this, around the hundreds of meters per second. So the mean thermal velocities tend to be quite large, even at room temperature. So it's a calculation that's worth having a look at just to get a sense for those. And that's the average speed at which the molecules are moving. Okay, and that's proportional to the temperature. So what we've described there is this kind of discrete molecular nature of the gas, and that's really what it is. But we don't use that in terms of fluid mechanics. When you did fluid mechanics, through all the stuff we've done so far, we have treated it as a continuum. And the whole idea of the continuum approach is that it's based on average values that do not contain significant fluctuations. So it has to capture macro variations, but be large enough to neglect molecular fluctuations. And a way to think this is in terms of a grid in computational fluid dynamics. So in CFD, we apply a grid to a domain. And if we take one of those grid cells, so let's say take that one there in the middle, we'd assign a temperature to that and a velocity to that. Okay, and that is assigned uniformly to that grid. And this continuum approach is a bit analogous to this in that if we want the grid size to be small enough that it captures all the detail of the flow, but if we have the grid too large, so say we go with a larger grid size that we take to be, say, this one here, that will now have gradients across it, so it will not properly resolve the detail of the flow. So you start to get these changes in the macroscopic variations. Okay, so spatial gradients, for example, in it, that wouldn't be captured. So your grid needs to be fine enough that essentially what you're representing is a point. But obviously, if you reduce it and reduce it and reduce it small and small and small, you end up coming down where the molecules which are entering and leaving the volume, and remember these are traveling quite fast, that there's an imbalance in those, and whether a molecule is in a region or not will greatly affect the quantity which you're ascribing to that region. So you see here, you start to see large fluctuations due to the presence or absence of molecules, or a high energy particle or molecule coming in and being present for the duration of the sample. Okay, so with continuum representations, we're sufficiently large that these molecular fluctuations are damped out, and we're able then to capture the macro variations. So it's sort of a sweet spot where the approximation works. Okay, and we ascribed differentials to these then. So we have the Navier-Stokes equations that work quite well. So these are continuum, and the whole domain is taken to be continuous, whereas in fact it's discrete. So really we're smoothing out all these microscopic fluctuations. Now, at what stage does the molecular effects really start to kick in? Well, a volume with about 10,000 molecules results in about a 1% fluctuation in macroscopic quantities. So if you have, for example, the temperature or the velocity or density of a region, if you've got about 10,000 molecules in there, you've got about 1% fluctuation in that parameter. And like for most purposes, that's sufficient. So that gives us a sense that our sample volume to molecular spacing should be about 22. Okay, so we can easily check that calculation and see how it was worked out. So if we're going to be talking about the length scale of a system, it needs to be much bigger than this. Okay, so the sample volume in this case would be with the same order as mean free path. So what we want is that we want to ensure we've got thermodynamic equilibrium. So what does that mean? So thermodynamic equilibrium requires the frequency of collisions in the sample volume to be high. And it's useful to think of this in terms of energy. So if this sample volume, this collision frequency is high, it means that a high energy molecule that comes in will undergo quite a lot of collisions, and therefore that energy will be distributed throughout the volume. So the energy level is dissipated. And don't be caught up here saying that this means there's no gradients. We will still have gradients existing between different samples and different spatial or temporal coordinates. So it's essentially, if you use this kind of a CFD grid analogy, I find that it's quite useful to try and understand this. So what we require, therefore, is that the mean free path must be small in relation to the sample volume, so that we need this large collision frequency. Okay, so what that is telling us is that the mean free path must be much less than the sample volume, that must be less than the length scale of the system. So we can define this parameter called the Knudsen number, which is the mean free path divided by the length scale of the system, and that must be less than 1. And that gives us our criteria for continuum flows. So if we're going to use the continuum approach, then the Knudsen number, defined by lambda over L, where lambda is the mean free path, must be very much less than 1. And if we're using, for example, a hard sphere model, this is our expression for the mean free path. Again, these are summarized in the table. They can be worked out from kinetic theory. So these are results from theoretical formulations. So you can calculate for a given pressure and temperature. So once the state is thermodynamically defined, we know what kind of fluid we have, so we know the viscosity. We can calculate what the mean free path is, and then determine, relative to the length scale of our system, whether the Knudsen number is sufficiently less than 1. Okay, that is very, very small. And if that is the case, then the continuum approach will be valid. So the Knudsen number really gives us a measure as to the level of molecular effects and their manifestation relative to our system. Now, with microsystems and microfluidics, we're reducing L. So L is getting smaller and smaller and smaller, which means that the Knudsen number is getting larger. Okay, so when this length scale is of the order of the mean free path, then we would expect the molecular effects to be really start to dominate. Okay, so we can use the Knudsen number to help us define where we are in terms of the validity of using a continuum approach. Now, the choice of scale is important because your scale needs to be representative of what's going on. So there's quite a famous paper by Gadel-Hack from 2000, it's nearly 20 years ago now. It was the Freeman Scholar Lecture. And what he argues is that you use this. And again, this looks a little bit hairy, but really what he's saying here is that this length scale he's proposing is the length scale over which the gradients in the system occur. So if you think about a fluid flow, you know, the gradients occur in the boundary layers. So delta, don't confuse this with the mean spacing, but the boundary thickness delta is normally used for that also, would be appropriate for that. Right, so what we get then is we can use a Knudsen number to define a range of regimes. Okay, and these are summarized here. So if our Knudsen number is less than 10 to the minus 3, then we have continuum flow. So Navier-Stokes would the no slip boundary condition. So zero velocity at the surfaces, at the walls. So that is the one that we're used to, and we've been dealing so far with in all our analysis. When your Knudsen number ranges from about 10 to the minus 3 up to about 0.1, now the molecular effects start to kick in, but they kick in the wall region. So that's where they become manifest, and you don't really see them anywhere else. So we have the Navier-Stokes with slip and temperature jump if you're dealing with heat transfer stuff. So what we're doing is we're still using the continuum approach, but we're modifying our boundary conditions. So we're used to doing the Navier-Stokes continuum with zero velocity at the wall, but now we bring in slip into the wall. So we approximate the molecular effects with a slip length, the definition of some kind of an interaction that allows us to modify the condition at the wall. If we're down between 0.1 and 10 of a Knudsen number, now the Navier-Stokes are pretty much gone. They don't really describe what's going on, and intermolecular collisions are important. So what's happening is the collisions between the molecules are becoming dominant. When a Knudsen number is greater than 10, then we're into a free molecular flow. And again, with this, if we look back at the definition, lambda over L, so the probability here is that a molecule will hit the wall of the channel before it hits another molecule. So there's a greater chance of it hitting the wall or a surface than there is of it hitting another gas molecule. So it's a very rarefied flow. There aren't a lot of molecules present. So the gas wall interactions dominate. Here in this regime, we're in what's called transition, but it's intermolecular collisions. So the chances are a molecule will hit another molecule, and that those collisions are what's dominating the fluid flow, the fluid behavior. Now, one thing you'll notice here is that when we look at continuum flows, we don't really care what the wall is made of. We don't say, oh, it was a steel wall or it was a plastic wall or whatever, what kind of pipe it was. We're not very interested in it. We get interested in the roughness of it for turbulent flow because that would affect the friction factor. For the laminar flow, we don't really care. Down here, we need to understand how the molecule interacts with the wall. So knowing what the wall is and what the gas is and how those two interact is what governs the fluid mechanics. Whereas up here, the wall has nothing to do with it. It's just zero velocity there. It provides a boundary condition. Here again, we're not very interested in it, but we need to understand in some kind of a model how we can modify the boundary condition to a slip condition to account for the interactions with the wall. Okay, so that's the key distinctions there. So this Knudsen number is a very useful parameter for allowing us develop a kind of a map of what models are appropriate to use. Now, in terms of what we've used so far, we've used that, and we're going to briefly look at this. That's slip flow, and that's as far as we're going to go. This other stuff I want you to be aware of. In terms of simulations, these use very different solution methods to what you use. Here we're still using continuum mechanics, we're using computational fluid dynamics. We're still using the same equations here, but we're modifying the boundary conditions. So we can still use the standard engineering tools here. In this regime down here, we're gone into molecular modeling. So it is much more, it's a much more different approach and uses different computational techniques. Okay, so there's a variety of modeling approaches that are out there. There's kinetic theory, direct simulation of Monte Carlo. It's a whole field in of itself. So we're into physics of flows here, vacuum stuff, and it's kind of outside our scope. So I just want you to be aware of that. There is a lot of work to extend the validity of the modeling strategies up here down to here, and to merge the two together and to use hybrid models and things like that. So it's a very active area of research. that we can blend and identify different regimes and use local models in one particular region, then move to a larger model in a different region. So that's as much as I'm going to say on that. Just be aware that it's a very extensive field. So what we're going to look at now is when we have a slip flow occurring. So that means that Knudsen number is less than about 0.1. And again, just bear in mind that these aren't hard and fast criteria. Okay, it's not that suddenly you're at 0.1 and you're in the slip flow, and then you're at 0.11 and you're in transition flow. These are guideline figures. Okay, so just be careful of that. Now, when we have slip occurring, what we want to do is we want to modify the boundary condition that we use. And the usual thing that we have is that the velocity of the wall is 0. So at any surface, the velocity of the fluid is 0. What we're now going to say is that we're going to tweak that. We're going to bring in a slip length. So there's two approaches we're going to use. One is based on Navier, and the other one is by Maxwell. So the Navier one gives us a slip boundary condition that is proportional to the wall normal gradient. Okay, so N here is the wall normal direction, and S is the flow direction. So this is our slip length. Okay, so it's got to have units of length. Put her here. So this is meters per second divided by direction. So by length scale. So this is a length scale to make this meters per second again. Okay, to cancel this portion here. Gradient. So very often we want to measure a slip coefficient or slip length and use that to define then what condition we have at the wall. The other approach is developed by Maxwell, and it's referred to as the TMAC. So it's a bit of a mouthful, tangential momentum accommodation coefficient. And what we have here is a more complicated definition. So this now is our boundary condition. Okay, we'll take stock of it. The first thing we have is that we have this thing sigma inside here. And sigma relates to how the molecules are accommodated at the wall. So sigma equals 0 means we've got a fully specular reflection. So 0 accommodation. That means that molecule here that hits the surface isn't held at the surface, just bounces off it, a bit like a ray of light. The opposite of that then is diffuse. Okay, and if you think of diffuse light or light hitting a diffuse surface, you would no longer be able to see through it or see an image from it. So the light is scattered everywhere. So for sigma equals 1, we've got a fully diffuse reflection. So the molecule or incident molecule comes in. So we have it here, hits the surface, and is held by the surface and then re-emitted in a random direction. Okay, so it may head off in any direction whatsoever. Okay, so that would be sigma equals 1, so it's a fully diffuse reflection. So that's referred to as full accommodation at the surface. And for specular, it's 0 accommodation. So it's not held and it's bounced off directly with equal angles here and here. And obviously real surfaces are somewhere in between this. So there's a specular component to it and a diffuse component to it also. So overall you get somewhere in between. Now let's take a second just to look at this. So we need to measure this, and this is a fluid material or surface property. So it depends, we need to know what the surface is and how these molecules interact with that surface. Okay, whereas previously we never cared about that whatsoever, and we just had 0 velocity at the wall. So again, you can see it shares a component where we have got a length here, which is our mean free path length, the Maxwellian version of it. So it's similar to the hard sphere model, a little bit different to it. And we have the wall normal gradient, which we had on the previous slide. So again, this wall normal gradient. Okay, we have this additional term here, which is linked to temperature gradient. And again, it's D2DSDN. And then we have this term back here, which I'll just change colors, green. And this is really interesting. Now, if you've got an isothermal surface, you don't need to worry about this. These terms are gone if you've got an isothermal surface. But if you have a temperature gradient, and the temperature gradient is in the flow direction, what this tells you is that without any pressure difference, you will have a flow. Again, slip will occur at the wall if you have a temperature gradient in the flow direction. So if I set up a system, I'll try to sketch it up here, where I have a surface, and this is T1, and this is T2, and I have a gradient in that, I will get a flow going along the wall. This has been observed and is observed physically in experiments. It's referred to as thermal transpiration. In fact, there's what's referred to as a Knudsen pump, is where people try to exploit this, to use this to pump fluids passively. So just by imposing temperature gradients on surfaces, that you get to pump. Now, what happens if you're pumping in a channel, and you've set up a microchannel with a gradient like this, you will get a flow that initiates along the wall. But as your flow moves, you end up increasing the pressure up here, and then you set up a pressure-driven flow that counteracts, and the two reach a balance. So you reach an equilibrium condition with that. So it's a really fascinating aspect to fluid mechanics, and some really kind of interesting effects. And again, it's an area that people are very interested to exploit in terms of technology. Also just understand better what happens with these flows. Key to this is being able to measure these things, and these can be measured, the TMACs can be measured directly or inferred from measurements. So we do measurements, we calculate what the flow is, and then we compare it to theory, and we figure then what TMAC is required to give us the flow, the bulk parameters that we've measured. So that would be an indirect measurement of it. From what I can see in the literature, the values for sigma vary, but they're usually not far off 1. And if you're in doubt, taking 0.9 seems to be quite a reasonable thing to do. There's one of the concerns with these measurements is that real engineering surfaces tend to be quite dirty, and they deteriorate in quality over time, and stuff deposits on them. And the effect of those deposits on these kind of flows, there's question marks over that. So quoted values for TMACs, if you look at particularly clean surfaces, rarely in service do they stay that clean. So you make a substantial change in your TMAC over the lifetime of the surface as it picks up deposits or gets contaminated. For example, if you touch it, you deposit oil in it, things like that. Okay, so it becomes very sensitive to those kind of things. Now, there's also a temperature jump that I won't dwell too much on. Again, there's a definition for it there. You can see that it's based on a wall normal temperature gradient. And sigma T is often referred to as the energy accommodation coefficient. Okay, so again, this is for when we have temperature gradients in place. Okay, so more for the heat transfer side of things. Now, you notice in this that what we have is essentially a first order term here. And so it's got a gradient. This term here is a little bit complicated, and usually it drops out and it's ignored. But here again, we've got dTds and dUSDN, so first order terms. And usually when people want to try and extend things, they increase the order, try and extend the validity of it. So you end up with higher order terms. But again, you end up with D2USDN squared. It's a bit of a mouthful to pronounce. But a second order differential here. And the accuracy of that you require in terms of resolving the velocity gradient to be able to get to a second order gradient out of it is quite onerous. So in practice, trying to get these high order terms is extremely difficult. So really, if you're going first order, I think that's fine. But when you start to go second order and higher, you're really pushing the boat. The more mathematical researchers tend to do it because they get perfect solutions to their stuff. When you're trying to measure stuff, you rarely have that level of precision, and it just becomes almost absurd to try and measure it. You can only do it under extremely idealized conditions. In terms of engineering conditions and engineering service, I don't see it being remotely practical. But there is a lot of work. Obviously, people are very interested in trying to extend models from here, which are relatively simple and work quite well, to try and push the limit of these, because to get into the computational stuff for the molecular flows is extremely challenging. It's computationally expensive. So being able to push the Navier-Stokes to the limits is desirable. So you will see models that have bring in second order terms into it. But I don't think it's a sensible approach personally. So we can see, for example, here, this is one done back in the 60s with Cersei Danny, where we have these second order terms brought in. Okay. Now, just in terms of channels, what does this mean? So if we're looking at slip flow and rectangular channels, what we have is we have this type of expression. And before we had it in terms of volumetric flow rate. Here we're talking about mass flow rate, because for gases, mass is more meaningful. Volume, due to pressure changes, takes on is less useful in terms of describing it. So this is our definition for the mass flow rate when we have no slip. So this would be our continuum model, where we've got this correction factor due to the sidewalls, due to the geometry. And what happens when we have slip is that, well, actually, you get more stuff going through it than you would expect, because it's slipping past the wall. So essentially, the velocity profile, if I sketch it here, we're used to the parabolic one. So I have that kind of a shape. Well, that should be a straight line here. Okay, so we have our parabolic velocity profile. But essentially now what happens is we have a bit of slip occurring at the wall. So we get this additional region here of extra flow going through. And the more slip we have, well, the more flow we get through it. So you're getting actually an enhanced delivery of fluid through your system. So it's actually beneficial. So we can modify this to account for slip. Okay, so this is a expression that we can use here. And this will give us the additional flow rate that we get. Okay. And again, Duan Muzichka in 2006 did a paper looking, so this Muzichka is the fellow who came up with that complicated correlation, general one that we looked at. So friction vector times Reynolds number squared root of the cross-section area. So again, the factor, so the actual mass flow rate compared to the no slip condition, the continuum approach is given by this. We have the TMAC inside there, the pressure ratio at inlet and outlet, and this parameter alpha, and there's a fit done to this parameter alpha here. So it can be defined as follows, and epsilon, which is used in this, is simply the aspect ratio as was defined previously. So if we have an arbitrarily shaped channel and we know what the TMAC is, for example, we can calculate then the enhanced flow rate that we would get through that. Okay, that concludes this lecture. It's the last one that we'll have. I plan to do kind of an open session that we'll try to do some Sulis and Big Blue Button, where just take some questions and talk you through maybe a past exam paper, just to show you the kind of stuff that I would expect you to be able to do. And just summarizing this lecture, I would expect you to understand about slip. So there are two different models, the TMAC and also the Navier slip length, which we have here. Okay, and also understand this regime here. Okay, and the use of the Knudsen number, what Knudsen number entails. Okay, thank you for your attention, and I'll send you out a message on when I'll have that session. I'll do it in one of the lecture slots. I think it's probably the most convenient. And if any questions, just touch base with me on email. Okay, thanks for listening. Talk to you soon. Bye bye.